And welcome back, everybody. This is a live picture looking out our window here at Breckenridge at the Doubletree Hotel. It is up to a whopping 18 degrees right now here in Breckenridge, up to headed to a high of 32. And tomorrow looks to be a bit milder as well. So maybe we'll see a bunch of skiers out there in the afternoon and just their ski outfit, no jackets or whatever. But it looks like a little mild day coming tomorrow. Our next speaker, following that powerful presentation from James Baylog with his wonderful visuals, we have Jim White, Dr. Jim White from University of Colorado. Jim has been associated with the conference here, the Weather and Climate Summit, for a long time, as Dale Eck from the Weather Channel and myself. And Jim, we have him come back just about every year because of his research that he's doing at the Institute for Arctic and Alpine Research at the University of Colorado. Jim spent a number of years studying ice up in Greenland, and looks like we'll continue to do that. He's seeing profound changes. Jim will talk to us about the science behind climate change, some of his observations, some of the latest research. And then after Jim's presentation, we'll take about a 5 to 10 minute break. We'll bring back Jim White and James Baylog to sit here and answer some of your questions online. And those of you who are watching or listening via Twitter, please submit some questions as well so you can ask those and get those answered. Tonight, starting at 6 o'clock Mountain Time, we're going to have a live town hall discussion about climate change, changes in the Arctic, and impacts it's having around the world and around the coastal areas and just about everywhere you can go. That'll be from 6 to 7 o'clock tonight here in Breckenridge, and we're inviting the town of Breckenridge to come in and participate in that discussion. We'll also have others online as well in the Hampton Roads community at Old Dominion University, which will be joining and watching live and submitting questions as well. And as you know, the Hampton Roads, Norfolk area is tremendously threatened by not only rising sea levels, but subsidence. The land is sinking. So with that, I'd like to give you an introductory video to Dr. Jim White, and then we'll kick right into his presentation. So take a look at this.
As a climate scientist, I do my work in Greenland and Antarctica because that's where the big ice sheets are. And we're seeing profound changes there. We're seeing melting of these large glaciers. I can tell you that big field work in Greenland, oddly enough, requires it to be very cold, because our ice is our archive, and so if it's not very cold, we lose our archive. And we've had to adjust over the last 20 years to the fact that it gets warmer and warmer in the summertime. We have trouble flying planes in and out because the snow gets too warm and melty and sticky. We have trouble doing our ice core processing. We have to dig down into the snow to do all that stuff. So oddly enough, we need to keep it cold in order to keep that archive working for us. So we've seen in Greenland and in the Arctic profound changes. The sea ice retreat of last year was just huge and an enormous wake-up call to all of us. Do human beings cause climate change? I will say yes, and I won't say anything more, because I don't need to say anything more. All right, I've answered your question, and I've not equivocated. I've not, given all the arm waving that I'm doing now. I'm just saying yes. All right. Now, as if you asked me that question as a scientist, are human beings causing climate change? I would go into all of the details, and how do we know that, and what are the uncertainties, and where are the areas? What's the soft underbelly of those uncertainties? Because that's what we do as scientists. We're always looking for the soft underbelly of our decisions. Where's the weak parts in that? I think if you do that with people, with the average person on the street, if you ask me, are human beings causing climate change? And I say, yes, but. As soon as I say but, I've lost the message that I want to convey. And the message I want to convey is that, yes, human beings are causing climate change. So we're in a situation where just from the raw number of people and the amount of resources we use, that we need more and more resources. We need more food, we need more water, we need more everything. What climate change is doing is compounding that problem. It's changing the baseline, if you will. If we need a certain amount of water in Africa or in Asia, and climate change reduces the total amount of water that's available, then that creates an additional problem on top of just the fact the population is increasing. Looking at these big problems that we face, I mean, in general, the problem of sustainability, how do we achieve sustainability, and all the subset underneath that of climate and water and food and all the resources, all the other issues. In looking at those big pictures, there are three actors that need to join together if we're really going to have solutions, effective solutions, and solutions that occur on a time scale that's useful. I mean, if solutions take hundreds of years, okay, that ain't going to work. And those three actors are the public, because they need to be educated and they need to put pressure on. They need to know what it's their planet after all. I mean, it's our common backyard. The second actor is the information gatherers, the scientists, the policymakers, the people who gather the information that the politicians, the policymakers and the politicians and the governments use to act on. So I think if you don't have those three actors agreeing and working together, then things aren't working very well. If we're serious about stopping it, we're going to be doing some things that today's generation never even heard of these terms. By the way, what is greenhouse gas geoengineering? Well, we're all going to know that in 10 or 15 years. This will be on the cover of Time. Easy prediction.
Welcome, everyone, to the 2015 edition of the Glen Gerberg Weather and Climate Summit. I'm Jim White. I'm one of the organizers of this conference, and very proud of what we've seen this year, very proud of what we've seen in years past. But I would like to remind everyone that all of these talks are archived online. You can go back and get whatever information you want in the past and also this year, and refer to these as the year goes by. So I'm going to follow up. Basically, you've had the filet mignon of Jim Baylog this morning. Now you're going to get, I can't even think of maybe Brussels sprouts. Maybe Brussels sprouts, yeah. Creme brulee. No, I don't think so. All right. Anyway, so spam. Spam. So, all right, for the next, 60 to 90 minutes, longer if you folks don't behave yourselves, you're going to get spam. I spent the last year giving quite a few public lectures and sort of I haven't reached Jim's booking agent kind of phase of life, but doing a lot in terms of talking with folks, both in large lecture formats. I gave the Niels Bohr lecture in Copenhagen to about 200 or 300 students there and faculty there. I just gave the NI lecture to 700 plus people at the American Geophysical Union. Stephenson lecture, and I gave a really interesting talk earlier this year to about 150 people in the oil and gas finance group in Denver. So one of my points in giving public talks is to go not only to the folks who really want to hear what I have to say, but also go places where it's a little more uncomfortable. And what I'm going to do today is give you sort of a mixture of many of these talks. And I'm going to start with some of the remarks I made at the oil and gas finance lecture, because what I tried to do there was find some common ground, find some ways that we could communicate without them immediately turning off or without me immediately getting annoyed. I will also draw on some materials. So last year, at the end of last year, we published, National Academy, National Research Council published a new report on abrupt climate change, and I'll loop back to some of that material. I would also point out that if you would like to see me in the National Ice Core Laboratory rapping, then just go online and find this National Geographic show, How to Make an Ice Cube. So there was actually some highlights, and so we went everywhere from the really sophisticated science to Jim White rapping about climate change in a freezer. Right? So we've talked about this before, but I think it's important to set the stage. Humans are really the largest agent of change on the planet. We are changing climate. We'll talk about that. We've talked about that. But some other metrics that I like to use, and I think many of you have seen this before. If you add up all the dirt that flows through all the rivers and streams of the world, plus all the dust that blows through the atmosphere, so you take the Amazon, the Nile, the Mississippi, the major rivers of the world, And then you compare that to the amount of dirt that we move in mining activities alone. We move 10 times more dirt every year than nature does. And then you add in all the other surface materials that we move around in building homes, shopping malls, etc., and the number is even more impressive. So when it comes to erosions, the natural way our planet functions is mountains are lifted up by plate tectonics, they erode back to the ocean, and that cycle continues. There's a rock cycle, there's a carbon cycle, there's all sorts of cycles in there. Human beings are the largest agent of cycling of material, of raw material on the planet, and by a large amount, by a factor of 10. The second one on the list I'll spend a moment to talk about too, because I've spoken this before, but I think this is really impressive. The way that this planet functions as far as we're concerned and the way it provides our needs is green plants figured out a long time ago how to take carbon dioxide, sunlight, nutrients, and water and turn that into sugars. Sugars are the basic food substance for us. Whether we eat those as Brussels sprouts or whether we eat those as Brussels sprouts fed to a pig and we have bacon, as we had this morning, that's the basis of where we get our food. Photosynthesis also, as a byproduct, produces oxygen. And without that, we as oxic creatures would not exist. So I told you you needed CO2, you need water, you need nutrients, and you need sunlight. Sunlight is in abundance. CO2 is in abundance. Water is frequently limiting, and that's, when you talk about climate change, really a lot of what we talk about and what Jim talked about and what I talk about is water. But nutrients are critical. Nutrients are things like phosphorus, nitrogen, micronutrients, calcium, potassium, etc., that plants need in order to build the molecules that we are eventually going to need. So, for example, DNA. You've got to have nitrogen to make amino acids and therefore to make DNA. Nitrogen is available to plants because bacteria out there take nitrogen out of the atmosphere. N2 is a very inert gas. It's a very strong bond. But they break that bond, and as a byproduct, they produce soluble forms of nitrogen, nitrate and ammonia, which they leave behind and which ends up in the water, going up through plant roots into the plant, and then allowing the plant to build these sophisticated molecules that we all need. So nitrogen is a critical part of us. I mean, without all those bacteria out there making nitrogen fertilizer, making nitrate and ammonia, we wouldn't exist. Up until the 1930s, that was all done naturally. That was all done by the bacteria on the planet, both in the land and in the ocean. In the 1930s, human beings figured out how to take nitrogen out of the atmosphere and chemically make that into nitrate and ammonia. We started getting into that in a very big way after World War II. And today, one very short generation later, we make more nitrate and ammonia than all the bacteria on land. So we went from really nothing in one of the most fundamental mechanisms of the planet to the point now where we equal all of those bacteria out there in terms of what we can do in terms of making fertilizer for ourselves. Now, that's got to have impact. Right? So how did this sneak up on us? How did we get to this point? The Admiral showed the other day a plot of population. Population is absolutely critical here, showing the increase, and the rate of increase is really important, recognizing that it took pretty much from 100,000 years ago to 1804 to reach 1 billion, but it only took about 10 years to go from 6 billion to 7 billion. So the time period between when you go when you add 1 billion has been shrinking remarkably. And that's really something that this generation has experienced in ways that previous generations have not. The other important part of this is the amount of resources that you need to run a complicated lifestyle. This happens to be per capita kilogram oil equivalent, or energy. It's not necessarily oil, it's coal, oil, and natural gas. I would point out that you can make these plots also for fresh water, for calories, food calories, for lithium, for batteries. There's all sorts of ways that you can scale this. But the point is that here's the world using a certain amount of energy. Here's higher income folks using something in the neighborhood of 4 or 5 times more, 3 to 5 times more than the world average. Here's the lower middle income folks down here, well below the world average. Middle income folks here somewhere obviously around the world average. The point is that if you are in a low income part of the population, and there are billions of people in that low-income part of the population. If they just want to go to the middle income, it's a factor of about 3.5. So 350% increase in energy and water and everything else in order to get to the middle income. And if your aspiration is to go from middle income, or from low income to high income, it's a factor of 7, so about 700% increase. So these are where population is increasing 1% or 2 every year. The world today is changing rapidly. China is industrializing. China's using energy at a much higher rate per capita than they did in the past. And it's not a question of a few percent increase. It's a question of 6-7% increase per year, or a doubling every 10 years in terms of the amount of energy that China uses. India is not far behind. The other 2 to 3 billion people on the planet who aren't there yet want to get there as well. And so this leads to what I call the nasty dilemma. We've talked about this before. We want others to live well. I talked to my undergraduates at CU about this, and I asked them, this is one of many ethical questions we're going to discuss here today. We want others to live well, and that's actually an interesting question to ask them. Do you want others to live well? But if they do, the energy and resource needs to do so will be staggering. That is really the critical issue of sustainability. We're hitting a wall here in terms of the planet's ability to provide us with the coal, oil, natural gas, or the energy we need, to provide us with the food calories, to provide us with the fresh water and all those other things. So there are many ways you can look at this. I love pictures of the Earth at night. You can get an app, Living Earth, where you can just look at the latest satellite composite of what the planet looks like, which is kind of neat because you actually see all the weather patterns. You can see lake effect snow in Buffalo and stuff like that. But what you can see today is very clearly showing us that human beings are a big, big thing on the planet. We light up the planet. The Earth at night is just lit up with lights around the world. And a creature that can do this is going to have impact on the planet. And really the question of sustainability is, how do we manage that impact in a way that favors us? Right? So I would point out that, you know, while I'm going to say lots of things about how important natural resources are and how important nature is to us, keep in mind that, you know, we're not going to, you know, mince words here. It's about human beings. You know, we are about creating an environment that's good for us on this planet. And we need to be honest about that. We need to think about that. We're not just here to make the planet really good and then turn it over to, you know, polar bears and seals and leopards. Some people maybe, I don't know. So all basic needs have environmental impacts. Arguing about how we manage those impacts is nothing new. We tend to view climate change as something which we haven't, you know, really gotten. It's some new thing where we're getting political and we're wrapping these things around the axle. If you go back and you look at the history of tetraethyl lead in gasoline, and you look at the history of that, it very much mirrors the debate that now exists about climate change and the use of fossil fuels versus the use of renewable energy. A lot of the same things happened. There were actors involved who had financial stake in this. There were scientists involved on both sides saying lead is not bad for you, lead is bad for you. We went back and forth. We spent about 50 years arguing about lead in gasoline, finally got rid of it. It's still very much in the environment. But it's really, the parallels in the argument are really striking if you go back and take a look at this. You can also find the same parallels in smog. You can find it in mercury. Mercury is still an ongoing argument today. Perchloroethylene is the stuff we use in dry cleaning. So all of these things have been through the same kind of arguments that we have today about greenhouse gases, climate change, etc. And it's interesting to note a couple of things. One is it takes about 40, 50 years for these arguments to play out. And the other is that you don't quite know how inevitable the result is going to be, but in almost all these cases, the early science that said, hey, this is a problem, pretty much holds up. And the reason why it holds up is that early on, folks tend to look at the simplest stuff, the basic physics. And when you look at the basic physics and you say to yourself, yeah, that makes sense, you know that those physics are still going to apply 50 years later after all the arguments are done. And eventually we'll come back to some decision that, yeah, we need to do something about that. I just pulled this up. I call this a good argument starter. This is lead exposure plotted against violent crime. And violent crime is lagged by about 20-something years. This was published recently. And there's actually some interesting arguments that are lurking here. Lead is a real problem for infant development in their brain. And the interesting and controversial way that one could look at this is that lead exposure led to a great deal of problems with children having issues with mental development, and then that then led to more violent crime in America. Cause and effect, we don't know. But these are the sorts of things where you first find these interesting little correlations and then start digging into them. Some of them will pan out, some of them won't. But if you want to get a good argument started, and I showed this to the oil and gas group, I said, if you guys want a really good argument, let's get into the effect of lead on children's development. So about after 20-something years of teaching courses and 30 years of studying past environments from ice cores, I have a few thoughts to share, and I want to start with language. I would argue that there are two sets of natural laws. I think I spoke about this a little bit last year, but I want to go into it a little bit more deeply. There's natural laws of what I call the second kind. These are laws, physical laws, the physics of chemistry, the physics of gravity, things like thermodynamics, the frequency of molecular vibrations. For example, carbon dioxide has a carbon in the middle, two oxygens here. The bonds, the masses of carbon atoms and oxygen atoms dictate a frequency of vibration. And all molecules express energy either by vibrating or by translating. I'm going to translate over here, or by rotating. That's the other way in which they express energy. But the vibrational frequencies are set by the masses of the atoms. And that's inherent to what the atom is. CO2 is the mass of carbon is carbon, right? If you change the mass, you can change it by 1 or 2 neutrons, but you've changed the protons, it's going to be nitrogen. There's going to be something else, right? So it's inherent in what that molecule is, the frequency of vibration, and the frequency of vibration dictates the energy that that molecule will absorb. So if you're a greenhouse gas, you absorb in the infrared, you absorb the Earth's outgoing radiation. If you are an ultraviolet absorber up in the high atmosphere, ozone, for example, you absorb higher frequency energy because your bond, the OOO frequency is such that you absorb higher frequencies of energy. That's physics, right? That's chemistry. You can't really change that stuff. That's what that is. There are natural laws of what I call the first kind, however, which are called value laws, morals and values. So things like what's good, what's bad, what's right, what's wrong. So murder, for example. Murder is outlawed around the world as a law of the first kind, where we say this is a value. We say you're not supposed to kill anybody. There's religious prescriptions against murder. There's all sorts of prescriptions against murder. That doesn't stop somebody from murdering somebody. All right? Murders happen every day. Large numbers of murders happen every day. So because there's a law against murder doesn't mean that murder stops. Right? Now that's an important distinction in law between a law that says you're not supposed to do it, but you can still do it. You may be punished for it, but you can still do it. Versus a law of the second kind, and we'll talk about this, which are laws that you really don't have any choice over. So a little quick comparison. The value laws, there's reasonable disagreement in terms of some applications. So murder's pretty obvious, but there are, today we see, we live in a world where a group that feels as though the publication of the Prophet Muhammad as a cartoon is an offense that should land you dead. Right? It's a group that firmly believes that, and there are groups that firmly believe that this is not the way to go. And there's a disagreement, and it's a religious disagreement. Okay? You can disobey value laws. You can believe or not believe in the core principle law. So you can believe that murder is wrong. You can also not believe that murder is wrong. You're allowed to do that. You may not be allowed to live in modern society and in polite society for very long, but you can certainly believe that. And the word law is applicable in what I would call the modern context. So when we understand law, we understand really value laws. Now, unfortunately, physical law, the word law was used for physical laws back in the 1700s, 1800s, and it's unfortunate because that word then gets convolved with the value law. Right? So there's basically universal agreement When we talk about gravity, we talk about gravity. The arguments about gravity, and there are arguments about gravity, are pretty esoteric. Right? You would not want me to give you a talk in this room on the arguments about gravity, because it's really deep in the weeds, as they say. You have no choice but to obey. Right? You don't get to wake up in the morning and say, gravity's not going to work for me today. I think I'll float around, and have fun today. Or I don't have to take the lift. I'm just going to kind of jump up in the air and spring my way up to the top of the hill. That'd be kind of a nice world, an interesting world. Belief is not a concept that applies. And Admiral Titley made this point the other day. Belief is not a concept that applies to physical laws. You don't believe in gravity, do you? I mean, maybe you do. I don't know. I can tell you, no, you don't. You don't get that choice. Right? Gravity exists whether you believe in it or not. Right? The frequency of vibration of CO2 is in the infrared whether you believe that molecule vibrates or not. Because that molecule could doesn't care. Whether or not you care about whether or not the frequency, it's going to vibrate in that frequency whether you believe in it or not. The belief is just not. I would argue the word law is misapplied. I would argue that what it does is it creates confusion. It gives us the impression that we can believe in something that belief doesn't really apply to. All right? So we sometimes confuse and mix these laws. We think we have a choice when we don't. But we also understand them very well at some times. So for example, I grew up in East Tennessee, and one of the revenue streams for the local communities was speeding. And we were very good at stopping the folks from Kentucky and Illinois and Indiana. And if you had Tennessee plates, somehow you managed to go past these things. I don't know how that works. But I think that's called a speed trap. And they would put the speed trap at the bottom of a hill. Makes a lot of sense. Somebody understood gravity. Right? Somebody understood that when you're in a car, also understood the tendency to just pull your foot off the gas pedal and let the car go down the hill, whatever speed. And if it happened to be a 30-mile-an-hour speed limit and you went 35, 40 miles an hour, you were going to get a speeding ticket. Right? So they understood that. That was something they understood in there, whether they would admit it or not. So the word law has contradictory meanings. And there's actually a term for this. It's called a contronym. In a physical law sense, as I pointed out here, we have no choice. In a value law sense, we do have choice. And so the word law holds within it a contradiction. We think we have a choice. We don't have a choice. And the problem is that the word law is used for two fundamentally different things. So my point is we often miss this contradiction and confuse laws. Now, there are many other contronyms out there. Rock is a contronym. So rock can either, if you look it up, it's either an immobile mass of stone, something solid, or shaking and unsettling motion. So rocking, you rock in an earthquake. So we say you rock in an earthquake, which gives you the impression that motion is going on, but then we say you're solid as a rock. Who was that? What song was that? Anyway. Exactly. I don't know who that was, but anyway, we ought to bring that up. Left is also a contronym. Peaches and herb. All right. So we managed to work peaches and herb into this talk, which, makes me a happy man. It's a first. That's a first. Left is a contronym. So left can either mean you remain behind, Howard was left, or departed. Howard departed. Right? So you can say Howard left. Right? So left, and my favorite contronym, there's a bunch of these, but my favorite one is fix. So fix can mean to repair or fix something, but fix also means to castrate. If you're a dog, this is a big contronym, right? Right? This is a big contronym, right? So we're accustomed to contronyms, but we're accustomed to many things that we don't think about on a conscious level, right? And this is, my point here is that we're accustomed to these sort of contronyms, but at the same time, we don't think about them deeply. We just push right through them. And that happens in the word law. So I'm going to point out two examples of things that I hear that I think exist because we make a mess out of the word law. And sometimes we think of it as something we can view as a first law sense, and sometimes we view as a second law sense. So one is fossil fuels are bad for the environment. I hate coal, oil, and natural gas. And I drove here from a warm home to tell you that. This is something I hear frequently, right? I teach a course on energy and the environment, and a lot of students come into that class with sort of the initial idea that coal, oil, and natural gas are the great evil, and how are we going to move forward from this? All right, so we'll talk about what gets messed up here. The other one is the one that the Admiral pointed out the other day. I don't believe in climate change. I think it's one of the classic mistakes that we made. And Jim, you made exactly the same point in your talk. So example one, I hate coal, oil, and natural gas, and I drove here from a warm home to tell you that. Here's somebody reading the facts of life now in the second law of thermodynamics. So energy cannot be created or destroyed, only converted from one form to another. That's thermodynamics. Physical laws tell us you can't get something for nothing. Right? That's an important point. We require energy. That's a physical law. And interesting value question is, can you hate that which you require? So hardly ever we hear people saying, I hate oxygen, I hate food, I hate water. And big question here is, have we become too disconnected from the planet that provides our needs? Because I think in some ways we have. In many ways, we don't even understand where our food comes from, where oxygen comes from, where water comes from, where our energy comes from. And we tend to not understand, therefore, when we run into issues with these things, why it is that we don't like some of these absolutely necessary things. So, interestingly, I hear people frequently saying, I don't, basically when they say I don't like fossil fuels, what they're saying is I don't like energy in today's world. Right? Now, we can dig a little deeper in that. But in reality, fossil fuels are 85% of our energy supply. They're excellent forms of energy for the cost. They're cheap, getting cheaper all the time, it seems. By the way, that won't last. Gas below $2 a gallon. Hang in there, folks. It'll be back up. What about other forms of energy, though? Can you hate a type of energy? And the answer is yes, you can certainly hate a type of energy. But be careful, because that just moves the problem down one level. And until you have that deeper understanding of where energy comes from, then you're still going to sort of hit the wall. And when I talk to the undergraduates, they don't know that 85% of their energy comes from fossil fuels. So when they talk about, I don't like fossil fuels, they don't understand that if getting rid of that tomorrow, which some of them would advocate, means really just a crash in everything that we do, because we need the energy to run the economy, to run the world. This is the consumption of energy by fuel type, just making the point I made, that liquids, which are oils, etc., coal, natural gas, these things are, and this is 2010 here, this is a projection by the Energy Information Agency going out into the future. We don't know that that's what's going to happen, but basically if you look here, renewables and nuclear, etc., down here, we use, 85% of what we do is coal, oil, and natural gas. So I want you to consider an analogy. Right? I tried this out on the oil and gas folks. America has an obesity problem. I think this is not a big-time news. We understand that. Humans require energy, which is a physical law. If you quit eating, you will die. And the reason is you metabolize sugars all the time in order to maintain the molecules in your body that you need, in order to have energy to move around. There's actually a lot of the energy you expend is just being, right? So just maintaining the systems you have requires a lot of energy. Right? Farmers supply those food calories. So basically, why don't we blame farmers for the obesity problem that we have? Right? They're the ones out there, they're the pushers, they're the ones growing the corn, they're the ones creating all of this food that is creating the obesity problem, right? So why aren't we out there picking on farmers? And it's interesting, because you think, well, I don't know. So with food, it seems as though people can separate the physical law imperatives, that is, you have to eat. What I get back from people when I say, why don't you blame farmers, is, well, I have to eat. Okay, I understand it. With our value law choices, that is what you eat and how much you eat. Right? So we understand, when it comes to food, we're capable of parsing that the value laws and the physical laws into two categories. Right? Now, one could make a simple analogy and argue that coal, oil, and natural gas companies are basically, and I would also add solar, wind, hydro, etc. These are all, the people who provide you with energy are energy farmers. They're out there producing the energy that you need. And interestingly, we blame energy suppliers, which are required by physical law, the limitations of physical laws, for our value law choices. We do this a lot. we tend to very actively pick on the fossil fuel industry in a way that we don't, for example, pick on the farmers. And I think Peter's going to get to this tomorrow, but there's a lot of reasons why we get into this, in part because I think the oil, coal, and gas industry, the energy farmers there, made some strategic choices that put them basically at odds with our needs, and put themselves, I think, in a position where they find themselves quite blamable for what's going on out there. So in part, I think the energy industry is to blame for the situation they find themselves in. But it's interesting because a lot of people simply don't get the point that we need all that energy, and that picking on coal, oil, and natural gas is kind of, when you think about it, does that really make all that much sense? Right? So there are value law choices. We can require that the impacts be managed. And this is where the argument gets a little bit more interesting. So for example, CO2 sequestration. You can build in more types of fuels that produce less carbon dioxide per molecule, like natural gas. So are there ways we can address the energy uses that we have? And I spent an entire 16 weeks a semester going through all these possible things here. So the second example I want to talk about is I don't believe in climate change. So this statement only makes sense if the basis of climate change is a value kind of law. So you don't get to believe, as I said, in physical laws. You can believe in value law. So let's examine, is climate change a value law system? And I think you're going to know the answer to this, but the answer is no. This is a set of slides that we've talked about in this room and in previous rooms before. And when it comes to global climate, forget about the details of Colorado, et cetera. Really, you only need to know three things about the Earth's energy system in order to know the climate of our planet. You need to know how much energy we get from the sun, which is a physical law. The sun radiates at a certain temperature band, turns out to be in the visible, if you're interested in the frequencies. That determines how much energy it produces. There's a certain distance we are from the sun, and all that determines how much energy we get from the sun. If you live on a lightly colored planet, you reflect more energy into outer space. If you live on a more darkly colored planet, you absorb more of that energy. So the reflectivity of the planet, what we call the albedo, is the second critical thing you need to know. And the only other thing you need to know the temperature of the planet is the amount of greenhouse gases in the atmosphere. This was apparent to folks back in the mid-1800s that the Earth was too far away from the sun to be as warm as we were. So they understood that there must be other ways in which energy is accumulated within the system. And that's when the whole concept of energy trapping by certain gases, people started to investigate that. So molecular vibrations is what this is all about. The Earth radiates in the infrared. Those molecular vibrations want to absorb the infrared, and so CO2 absorbs some of the outgoing radiation of the Earth, basically increases the amount of energy in the lower atmosphere. The energy in the lower atmosphere is the climate system. And if you don't believe that molecular vibrations can are real, think of swing sets, think of somebody trying to break a glass with their voice. You can actually do this. What they're doing is they're putting out a frequency in their voice which matches the frequency of vibration of that glass. And you can actually, I've seen these things in slow motion. It's really kind of cool. The glass just starts to absorb the energy, oscillate more and more and more, and then because it's glass, if it's CO2, it absorbs it and then re-radiates it. So the Earth's temperature without greenhouse gases, we know from either measuring at the top of the atmosphere or by just calculating how much is up there, is about -18. It's certainly too cold for advanced life. These are all in Celsius. The Earth's temperature with greenhouse gases is about +15. And the difference is greenhouse gases. So greenhouse gas, so having an atmosphere, which includes greenhouse gases, and by the way, water vapor is the #1 greenhouse gas. So any planet that has water on it, liquid water on it, is going to have a greenhouse effect. So if you're looking for the Goldilocks distance for a planet from a sun, you want to look at a planet that's far enough away that would actually be frozen, and then you add water into the equation and it raises the temperature up. Right? So you got to find that sweet spot, and that sweet spot this is what astrophysicists do all the time. So greenhouse gases raise the temperature of the Earth by about 33 degrees Celsius, or about 60 degrees Fahrenheit, and I certainly would argue make the planet habitable. So this is an important thing for us to understand. So if we add lots of greenhouse gases to the atmosphere, and Jim showed you a plot of CO2, you can also see methane is tripled in the atmosphere. CO2 is up by about 30%. Nitrous oxide, another biggie, is up by about 30%. Some of them, like Chlorofluorocarbons didn't exist. They're not natural compounds in the past, and so they're up by infinite percent. But in general, we've increased the amount of ability of the atmosphere to absorb energy by about 40%. So if you had lots of greenhouse gases in the atmosphere, and I would argue 40% is a pretty big number, there will be more energy in the atmosphere, and by definition, climate change will occur. So it is a physical law of limitation. You don't get a choice in this. So when we put greenhouse gases in the atmosphere, we help the atmosphere to trap more energy, and that will change climate. Right? So to argue about whether or not climate change is real, or just say I believe or don't believe in climate change is really, like I said, you don't get that choice. Climate change is real. Human beings are causing it. Really, the question is, how does one then go about dealing with these sorts of things? So climate change will happen. There are some upsides, there are some downsides. So it's worth actually going through some interesting thoughts here. Some upsides, the planet will continue to function because it has been warm before, and greenhouse gases have been quite high in the atmosphere in the past. We don't think that adding a lot of CO2 to the atmosphere, for example, is going to cause photosynthesis to have trouble. Or we don't think that, we know that there are thresholds that green plants can reach, at which it's so warm that they respire more energy than they can accumulate through photosynthesis. So there's a limit, a temperature limit on a planet where you can have green plants. But that limit is pretty high. It's about 40 degrees Celsius. It's up there. It's likely to have higher plant productivity because you put more CO2 in the atmosphere, you have longer growing seasons, all the other things, you're going to have more plant productivity. Globally, there'll be more precipitation, and that's because if you look at, you guys know this, how energy is distributed in the atmosphere, about half of it goes to sensible heat, about 30–40% goes to evaporation. So you're in business because a good chunk of that energy goes to evaporate water, which then has to fall back out of the atmosphere because the atmosphere reaches saturation. And if you warm a planet up, you get more precipitation. Now, that may not be precipitation where you want it, but globally you get more precipitation. Areas once inhospitable, and I'll talk more about this, will be reachable. The Arctic is actually an interesting, we live in interesting times. If you go back 100 years or 200 years, there were parts of the planet where people were still exploring. Lots of Alaska, lots of Russia were still places where people had not been. They had not been there 200 years ago. They were just beginning to wander through some of these areas. Right? The Arctic's been sort of like off limits. It's been so cold, so frozen, we haven't been there. It's now becoming not so cold and not so frozen. And really, for the first time ever, we have a sophisticated society which has a new chunk of a planet to explore. You don't have to go to Mars to find new areas to explore. The Arctic is becoming a new area to explore. We are adaptable. We've already adapted. Go on and on. So there's certainly some downsides. We've heard a lot about this over the years. Changes in weather patterns threaten to decrease our food and water supplies. So it is true that we set up our agricultural systems around the temperature and precipitation patterns that are out there today. So you grow corn where corn will grow. You grow wheat where wheat will grow. And they grow in areas where you have the right temperatures and you have the right precipitation amounts falling in the right seasons. Okay, so we've tailored the planet to the climate, and as the Admiral showed the other day, the climate of the last 10,000 years has been relatively constant. We have parsed the planet out into countries. And what that means is that as the baseline changes, as climate changes, there will be winners and losers. So some areas will do better in terms of growing food, having fresh water. Some areas will do worse in terms of having fresh water, having food. This creates conflict. This is why when the Admiral talked about this, why the Pentagon cares about this, why the Pentagon is our number one federal agency when it comes to spending money on climate change is the Pentagon, because they understand that as the system changes out from underneath us, and as the borders of the countries that we set up don't change, then we're going to have winners and we're going to have losers. I'll talk more about this, but the pace of change can be beyond the ability for natural adaptation. So ocean acidification is a very big problem that you folks ought to be aware of, in large part because acidification is happening so rapidly that we don't know how the ecosystems of the ocean are going to respond. Yes, in the past, 60 million years ago, CO2 was much higher than it is today. And what that means is the oceans were more acidic than they are today, because CO2, we'll have to go into the details of that. But yes, the oceans were more acidic. There were corals, there were shell-forming organisms, but the question is, where were they? How were they living? Were there refugia around where fresh water came in? Were there other areas where you were able to have shell-forming organisms that hung on in a more acidic ocean or changed, adapted? So changes in their molecular structure made them capable of forming those organisms under a more, forming those shells under a more acidic ocean. The speed with which we're changing CO2, so the speed with which the ocean is acidifying, is a real fundamental problem. It doesn't give organisms enough time, we're afraid, to make those kind of changes. And that's really one of the reasons why we're very, very interested in this. It's the reason why species are going extinct, because of climate. Species also go extinct because we use the surface of the planet in ways that are incompatible with them. But speed is also really important when it comes to species extinction. How rapidly it changes in temperature space, how rapidly it changes in water space, how rapidly things evolve can affect species. There's certainly less water for a thirsty Western U.S. We've talked about this. It's very important in these areas. Interestingly, I'll mention this now, we can come back to it. If you go back 3 million years ago, when the Earth last had 400 parts per million CO2, it was a very much warmer planet. There were trees growing all the way to the top of the Arctic Circle in Canada, and it was rainier here. There was more precipitation here in the West than there is today. And so, but we don't know how it goes from point A to point B. How do you go from a climate which is yet to reflect 400 parts per million CO2, and we'll talk about that, to a climate that reflects 400 parts per million CO2? What's the ride along the way? There could be lots of really low moisture points along the way, or really high moisture points along the way. We don't know. Right? And higher sea level being very costly, very disruptive. We'll come back to that. So I now want to switch gears a little bit and talk about abrupt change, because I think abrupt change is one of the key parts of the climate system that is we don't hear enough about. And it's, as I pointed out with ocean acidification, this is one of the key problems that we have. How rapidly things change can make a big difference to how we're able to adapt to that. We're in the midst of a climate change, so how climate change occurs will be critical. And as I point out here, in adapting to change, speed kills. So understanding and preparing for abrupt change is critical. There is no universally accepted definition of abrupt change, but in general, it's got to be fast. So it's got to be less than human lifetime, because we measure things by how humans think about these things. It's got to be big. It's got to be big enough for us to recognize, whether it's a change in average, whether it's a change in variability, it's got to be big enough for us to recognize. And the change seems to be out of proportion relative to the suspected cause. So for example, here is in Moon Lake, North Dakota, you see this is deviation from mean log salinity, so basically how fresh this lake is. It was cruising along for about 1,000 years with a certain pattern of variability. That pattern of variability changed very abruptly in the 1300s or so, and this lake now goes through much larger swings of amount of moisture that flows into the lake. So that's a big abrupt change in variability in this particular system. We can come back to this, but so there's a new report that came out. This is online. It's free. Taxpayer dollars at work. Feel free to download it. It also considers abrupt climate impacts. So one of the things that we know now is that it's not just about the climate system changing, not just about how much temperature changes or how much precipitation changes or the seasonality or something about that, but a slowly changing temperature can trigger abrupt shifts in other systems. And we have many systems that rely on or are connected with the climate system. One of the examples I've used in the past, and I believe I've used it with you folks, is while I was writing this report, I got a call from someone in the air conditioning industry who wanted to know what would be the average temperature in some specific part of the world in 30 years. And what would be the high temperatures, the average, what kind of high temperatures would this area be seeing in about 30 years down the road? And as I dug into the question a little bit more, I realized that this is somebody in the air conditioning industry who makes very large air conditioners for very large server farms, think Microsoft, Google, etc. So these are very large, very power consumptive systems that need large air conditioners to cool them off. And when they build those air conditioners, they want them to last for 30 years because that's what the federal government says. It's actually 29, I don't know why. But you can write off your air conditioner over 29 years. Right? So if the air conditioner doesn't last for 29 years, you've lost money. Well, as it turns out, air conditioning systems that were built in the 80s and the 90s, particularly in the 90s, they didn't anticipate that the baseline of temperature would be changing. And so some of these air conditioning systems are failing after about 15 years. And so, you know, pick a number, a $50 million air conditioning system, which should have lasted 30 years, is only lasting 15 years. And this is a pretty big financial hit for a company. They don't want to see this happen. So they're actually now recognizing that as the baseline changes, they have to plan for that in the future. So this is a threshold in the system that was crossed by a steadily changing environmental system. There are many of these. I just gave you the air conditioning example, the New York City subway example. I put a question mark here because we don't know everything there is to know about Sandy. But what we do know is that Sandy was the first time that the floodwaters pushed above the height of the entrance to the subway system. There's a threshold, a very real threshold in the New York City system. And you can see here, this is the height above sea level for a bunch of storm surges in the past going from the 1950s. Here's Sandy, and a lot of these got close. They didn't quite make it, but when Sandy hit that threshold, what was probably going to be a $1 billion problem turned into a 30, 40, 50, in the end it was something like a $60 billion problem. So the thresholds in our systems are very real. I'm going to skip this. We can come back to that. But these tipping points aren't always clear. So abrupt change is a common and natural feature of the climate system up until the 1990s. We thought of the climate change as gradual. So when I was a graduate student, probably when Peter, we took the same courses, you know, we learned about Milankovitch, we learned about slow changes in the system, we learned about thousands of years of change. And really, we began to publish papers about abrupt change in the late 1980s, early 1990s. So this is a very new part of the system. And I will point out that, and I gave, this is part of the Niels Bohr lecture I gave, Greenland ice cores and ocean sediment certainly changed that view. So Jim showed you a map of Greenland where all his cameras are. By the way, up here in the corner is where we hope to go with our next big ice core. This is an ice stream. So ice streams are features in which ice is flowing very rapidly. In this part of Greenland, ice is flowing at about 90 meters a year, which is, you don't think about when you're there, because everything is moving 90 meters a year. But if you put out a bunch of stakes across the front of a glacier that's moving that rapidly, you can actually sit there and watch over time, over a month or so, watch those stakes move, and the whole thing bows and bends, and out it goes. These are areas where ice is flowing rapidly. These are areas where we think sea level rise can be impacted by glaciers much faster than in other parts of the world. And you saw the impacts of this very visually in Jim's talk. Abrupt events are a very natural part of our climate system. The green things you see here are abrupt changes in temperature. We've talked about this in the past. Large increases in temperature. Think Miami to Montreal occurring in less than a human lifetime. That kind of abrupt. We first, as I said, went after this in an ice core in 1989. We published a paper looking at this last time it was really cold, called the Younger Dryas. And we pointed out in that paper, this is from Nature in 1989, we pointed out that there was about a 15 degree, it's about 10 degrees actually, increase in temperature over about 50 years. There were other parts of the system that changed even faster in about 20 years. And I remember having large debates with my co-authors, Willy Dansgaard and Sigfús Jansson, who are both deceased and therefore can't argue with me now, but the argument about whether or not 20 years, whether or not it was even faster than 20 years. And we didn't think people would believe 20 years, so we made it 20, thinking that if we actually made it 4 or 5, which we actually think it probably was, that no one would believe it anyway. So as it turns out, the story evolved over time. These things are real. There's a whole bunch of other things that happen. Snow doubles in 1 to 3 years. Sea ice proxies we have, large retreats of sea ice in the North Atlantic in 1 to 2 years. Methane went up by 50%. No humans involved in 50 years. Nitrous oxide went up about 10% in 50 years. So large changes in our climate systems naturally occurring in very short periods of time. We've gotten to now where abrupt is even more abrupt than we thought it was. So for example, this is a measure, this is called the Cheermx, but it's basically a measure of what the ocean was doing out in the North Atlantic. We have a bunch of cores. We can now synchronize them with volcanic events so the volcanic event has to be synchronous. So we don't have to use the date itself to synchronize these things. And you can see that this is basically a plot telling you that for thousands of years, the Earth was operating under one system. And then in about 1 to 2 years, it shifted to a new regime, in this case, large decrease or increase in sea ice, and then it stayed like that for 1,000 years. So what we found is that the Earth system contains these thresholds, and these are quite obvious thresholds. And I said, we'll be cruising along thousands of years at a certain level, and then in a very short period of time, shift and then stay for thousands of years at that new level. We know, for example, that I told you a 10-degree change in a human lifetime of 50 years. We now know that that's really occurring in 2 steps of about 1 degree per year for about 5 years, 1 degree Celsius per year. So we've had basically 1 degree Celsius in the last 100 years. That's the warming that we're all talking about these days. So these things are 100 times faster than what we've seen in the last 100 years. And these things have happened frequently within the system. They basically represent a reorganization of atmospheric circulation, a reorganization of ocean circulation in ways that, those of you behind the camera that'd be like a holy shit moment, right? Something's happening.
What's the x-axis on these?
Oh, on these? So this is years. So that's 11,500 years ago to 12,000 years ago. That's a 500-year axis right there. I can get more into detail, but so in ice cores, we can actually go down to the year, 11,000 years ago. It gets even more interesting in that we've now been to northern Greenland here a couple times. We've been able to document large changes. This is a 10-degree step change in temperature, which occurred in about 1 to 2 years. So that infers a warming rate of 5 to 10 degrees C per year at this location. Doesn't happen everywhere. But this is one of these places where probably was some atmospheric circulation threshold, and when it passed this location, boom, it just passed this location. That's 1,000 times faster than the current warming. I'll skip that. I would point out that abrupt change is just not something you see in the past. We see it today. There's a bunch of ways in which we see abrupt change. We go into detail in this in our report, but I'm going to focus on Arctic sea ice and groundwater loss. So Arctic sea ice is going away. This is something we've talked about, something I think you folks, we have to bring Jennifer back and have an update on where the debate is on this topic. But as the Arctic is becoming more and more ice-free, how much of an impact does that have on the weather that we have down here at 30, 40, 50 degrees north? Certainly a big impact on Arctic ecosystems, certainly a big impact on shipping, on coastal erosion. Coastal erosion is actually really interesting, and I don't have the movies, but for example, almost all of these places are a mixture of ice and rock on the coastlines. This is frozen material, this is permafrost. And as that melts, erosion, which was nibbling away at these frozen features, now just takes away meters of coastline in one storm. And so you can see, a half a mile of Alaska going into the ocean over a period of about a half a week in some cases, where you got enough melt back and just oomph, huge slough of material off into the ocean. Certainly faster than anticipated. Admiral Tittney showed you this, but I want to show it to you again and just make a different point than what he was talking about, the decrease in ice. The decrease in the age of the ice. I want to point out that what's really important about this is that old ice is ice that can withstand change. So the way the Arctic normally works, it has worked for thousands of years, is it's cold enough that old ice forms every year, and old ice is ejected out into the Atlantic every year. As long as there's a balance between what's lost and what's gained, you maintain these big ice masses up in the Arctic. What's been happening over the last 30, 40 years is that the old ice has been ejected, and it's not been warm enough to form the new thick ice. In 2007, you saw there, in 2012 are 2 big years in which this is an episodic kind of thing, in which old ice is ejected. So now what we have, now this is still ice today. It's frozen over, but it's mostly one-year ice. And that's, if you go back to the 1970s, 1980s, it was mostly multi-year ice. Multi-year ice can withstand a warm summer. One-year ice, not so sure. Definitely melting back from the coasts here, melting back from the coasts here. Interestingly, it'll be what they call the Northwest Passage, which will probably still be clogged up with multi-year ice. It's really, I think, as the Admiral pointed out, going to be more of a sailing across the North Pole kind of situation. But this is something that we've talked about in the past. I want to make this point that ice can go away very rapidly, lake ice or sea ice. This is Lake Erie on February 27th of 1973. It's 100% covered with lake ice. Lake Erie is about 27,000 square kilometers, which is the size of Massachusetts, or if you grew up when I grew up measuring everything in the size of Rhode Island, this is 6.8 Rhode Islands. About 2 weeks later, on March 13th, 1973, Lake Erie's melted out. So this happens because the atmosphere warms up, because the water's warm, winds come along and begin to stir things up. And so we know this. If you live in an area, you live in Minnesota, places where you have lake ice, you know that that ice can change very rapidly. And this is what we're worried about in the Arctic. When we have a very warm summer with the right meteorological conditions, you got the high in the right place, shoving the winds out there, pushing the ice out, you could free up a lot of the Arctic and change white ice. Remember, reflectivity is the second thing you need to know about the temperature of the planet. You trade white ice for blue water, and you change the amount of energy absorption up there quite remarkably. And how that then impacts, as Francis would tell you, how that impacts the jet stream, how that impacts the speed of storms, etc., is a subject of a lot of debate. But it's something that you all need to keep your eyes on. Because when we start to get, and we will start to get these summers with less and less Arctic sea ice, keep an eye on this. Are we starting to see strange weather phenomenon, or stranger than what has been happening? Right? I pointed this earlier, but basically the Arctic is the part of the planet that will be settled, the part of the planet that will be explored, the part of the planet that will be exploited. There are native populations up there who are already just nervous as hell that all of us folks from down here at 30 degrees are going to go moving up there and make a mess out of their lives. We have a long history of that, so they have reason to be nervous. This is a plot. There's many ways of measuring this. The redder the color, the more the human footprint. There are many ways of measuring human footprint on the planet. But note that areas where we cannot inhabit very well, there's not much of a human. This is habitable and becoming more and more habitable as time goes by. Northern Canada, particularly Russia has huge amounts of territory that will be habitable, exploitable as time goes by. I would also point out there's been abrupt changes in other parts of the system. I could tell you a lot about ecosystem change, about species extinction, but groundwater is really important. I think I might have mentioned this before. This is a plot of changes in gravity over 10 years, from 2000 to 2010, so the gravity satellite system, the GRACE system. When this was put up, it was a bunch of geophysicists really interested in the geekiness of micro changes in gravity. Turns out that the major reason why gravity changes over terrestrial areas is how much water's in the ground. So you put more water in the ground, there's more mass. You got more mass, you weigh more. Right? So by tracking the trends in gravity over land areas, we were actually able to track changes in groundwater. This is a very, very difficult thing to do otherwise. There's a few places in the world, the Ogallala being one of those, where we have seen groundwater tables drop precipitously, where we now have a bunch of wells out there, and we spend a lot of money monitoring this. But there are very few places on the planet where that's done. And the ability to measure this by satellite is a huge breakthrough. And we should have even better satellites that do this even better. Right now, the resolution's pretty coarse. But you see where the depletions are. The redder colors and the yellow colors are where depletions are. These are areas where groundwater is being taken out faster than it's coming in. In other words, mass is decreasing here. So the grain-growing part of the planet. So here we are in the United States. You go across to Europe, to Russia, etc., China. These are where corn, wheat, etc., the breadbasket of the world, is an area where water is being drawn down very rapidly. And we're now able to see that. We're now able to understand that. There are parts where you're getting more rainfall, and you see the build up there. You also see Amazon drought, etc. The big droughts in Australia. For the U.S., an interesting bullseye of water removal here in the southeast. Brad and I were talking about this earlier. You know, the southeast is one of the few areas that's actually not warmed up like the rest of the planet has. And there's some really interesting questions about why that is true. And one, this was Brad's idea, one possibility is it's actually getting drier there. And as it gets drier, you don't see the temperatures being ameliorated by the humidity in the atmosphere as much as you would otherwise, and if it cool off a little bit more at night. This is, I mean, you folks are from, some of you from Atlanta know that it rains here. I mean, it's not like it's drought here, but the amount of water that's used in that area relative to the amount of water that falls is not large enough, and so we draw water out of the ground. This is really critical for food. So in the farming communities, if you want to get by in a drought, you take water out of the ground. There was a time when we would save grain and if you had excess milk, you turn it into dairy or to cheese, and you stored the cheese. I grew up in East Tennessee. We had gummet cheese. That was part of our lunchtime adventure. That and boiled everything else. But this is not something we do anymore. We don't save in years of plenty and then put that back out on the market. It's pretty much a just-in-time food kind of situation. And so if you don't have groundwater, you can't make it through droughts. And if you're not going to grow the grain here, you're going to have to find other places to grow it. And as you can see, we live on an asymmetric planet. You know, the northern hemisphere's got the land. That's where you can grow the grain. It's not like you have a whole bunch of southern hemisphere that you can now pull into play, saying, okay, it's raining enough in the southern hemisphere, we'll grow corn, wheat, et cetera, down there. Also keep in mind the fact that we parse the world up into countries, which makes it much more difficult to actually have that kind of global cooperation. So there are many thresholds of interest out there. I want to spend some time talking about sea level rise rate, because I think that this is an interesting problem. And I would point out sea level rise is, if you look at what I call the inevitability factor of change for the future. So there's really three things you need to know about change as time goes by. You need to know how big a change is going to be, you know how fast it is. You need to know how inevitable it is. So if something is not terribly inevitable, then you can sort of balance, am I going to get worried about this? Am I not going to get worried about this? Even if it may be a big change, the probability may be so low that you don't have to worry about it. Sea level rise happens to be one of those things that's big, it's inevitable, but it's slow. All right, so let's talk a little bit about that. Now, what do I mean by big? This is a plot showing the amount of CO2 in the atmosphere and the sea level for the last 500,000 years. We really were only able to make such plots maybe 20 years ago when we had the beginnings of ice core CO2 records and enough measurements of sea level. It's a big, long lecture on how we get sea level, but there's enough measurements of sea level going back in time that we can actually make this plot. But note that what this shows us is that the Earth goes through periods of interglacials and periods of glacial periods. You can also put temperature on here. It also maps very, very closely to this. Note the scaling, though. CO2 changes by about 100 parts per million. 400 is up here somewhere. Sea level changes by about 130 meters. And that's an important, so there are, I think, some big physical lessons that we need to learn as occupants of the planet. And one of those physical lessons is that sea level changes by large amounts on our planet. Not small amounts, large amounts. And so over the last 500,000 years, sea level has gone up by 400 feet, up and down by 400 feet, which is a large number. And particularly when you think about sea level has risen by about a foot over the last 100 years, and we're already seeing in many places of the world problems with that. So that's 1/400th of the dynamic range of what the planet is capable of. So it's a very small fraction of what the planet is capable of. So here's some, I use Florida here because I love to pick on Florida. So it's interesting. So if seas were lowered 400 feet, this is what Florida looks like. So there's huge tax opportunities out here, large, orange groves, etc. About 20,000 years ago, the Neanderthals and the other humanoids which were present, had big, there was large chains of golf courses, proto golf courses. They hit rocks, which was, so they weren't able to do, the kind of sophistication we have today. But this is about twice the size of Florida. This is Florida with about 170 feet of sea level rise, which would be if you melted all of Antarctica, all of Greenland. And it's basically gone, with the exception of Tallahassee. So I'll talk more about that. That's one of the reasons. This gives you an idea of how dynamic sea level is. And this has occurred, right? So this is not something we just make up here. So the rate of sea level rise is currently such that we expect about 1 meter or 3 feet by 2100. But I would point out that when we looked at the rate of sea level rise in the record, rates of 3 to 5 times faster than that are pretty common. So the rise rate of sea level today is mostly dictated by the warming of the oceans, which is absorbing about 90% of the heat, and so thermal expansion, and by the melting of mountain glaciers. And Jim noted this in one of his slides. Mostly mountain glaciers are doing a lot of that lift. Greenland and Antarctica are kicking in, but they can kick in much bigger than they have so far. So 3 feet of sea level rise in 100 years is pretty easy in the Earth system. 10 feet in 100 years, or as I would point out here, the difference between 1 meter in 100 years is fundamentally different than 1 meter in 30 years. 1 meter, 3 feet in 30 years, 3 feet in a mortgage, if I would put it in those terms, is fundamentally different than 3 feet in 100 years. All right, so I did talk about that. I won't talk about it anymore. When I was preparing this lecture for the folks in Copenhagen, I was reading a bunch of newspapers online. This is the Washington Post. So this is Miami Beach Mayor Philip Levine said, Miami Beach is too valuable to lose, with real estate worth more than $23 billion and tourism revenue of over $9 billion a year. That was in the Washington Post on the 23rd of April, 2014. Sorry. There's not much you can do. The billions of dollars in Miami Beach isn't going to stop sea level rise, right? And that is one of those physical realities that you have to get used to. And I applaud. Miami Beach has been at the forefront of complaining and saying, hey, we need to do something about this because they've got all this wealth tied up in this area. But the reality is that this is going to be a struggle. Miami Beach doesn't have much of a future as time goes by, and because sea level is rising and will continue to rise. Now, sea level can rise even faster. And one of the reasons is that many of the world's ice sheets are not what we call rock-based or land-based, they're marine-based. So this is a map of the bedrock of Antarctica, and one of the areas that I work in a lot these days is trying to understand how wet, so this is all ice here today, but the base of this ice sheet is as much as, here's 10,000 feet, is as much as 10,000 feet below sea level. So this is an ice sheet that is almost all below sea level at its base, and large chunks of East Antarctica as well. So there's a large amount of ice out there in the world that has at its base ice below sea level, and that's fundamentally unstable ice because ice likes to float. We all saw that in Jim's talk. This is the reason why we're going to the Northeast Greenland ice stream. It drains into one of these areas where ice is below sea level. That creates an issue, what we call grounding line. So the ice stays there because the ice hits a rock point, stays there. And as warm ocean currents come in and erode this point, and as sea level rises and destabilizes this point, we face a situation in which there's really not much stopping that ice then from coming out at basically whatever the physics of ice flow tell us is the fastest rate that ice can flow. Now I'm going to go back to the previous slide because the ice that Jim showed you that was pouring out on the west coast of Greenland is constrained by rocks. Right? It's like the mouth of a river. It can only get out as fast as the rocks on the side of that is going to allow it to happen. In marine-based areas, the throats here where ice can flow out are enormous. They're hundreds of kilometers. And so imagine a river that no longer has a constraint in terms of its banks. And there's a whole bunch of water backed up behind there that wants to get out. That's the situation we find ourselves in with these marine-based ice sheets. And there were a couple of articles this year that talked about a group at Washington and a group at Irvine talking about this ice beginning to flow out of West Antarctica. And they talked in terms of inevitability. They talked in terms of it's happening now and it's not going to be stoppable. So it's just going to continue for ice to flow. And this inevitability factor is something that we're just really coming to grips with and trying to understand better than we understand today. And as I would point out that as the ice flows out, even if it's, say 4, 5, 6 feet in 100 years, there's points along the way in the human system that are abrupt points. So the Federal Flood Insurance Program. Today, Congress tried to make that, a payer pays system. That failed. We're back to all of us paying into the pot to support the Federal Flood Insurance Program. There's multiple trillions of dollars of stuff at risk along coastlines. And this system doesn't have anywhere near the amount of money in it to handle that. So this is a tipping point. We'll be arguing about this as time goes by. I mean, we argue about Medicare, Medicaid, Social Security, et cetera. This is going to be an interesting federally backed system that isn't going to be able to handle the payouts relative to what goes in. Property values. Property values are a big problem. These are highly nonlinear things. When people think they can no longer sell their house on the beach, and they sell lower than they were otherwise, and people kind of catch on to that, property values sink very rapidly. We've seen this happen in other places where houses were either at earthquake risk or at flood risk. Key infrastructure and fresh water. So key infrastructure meaning sewer systems and electrical systems, et cetera. Roads that are located in areas that are becoming more and more flooded. And then fresh water. Many of these coastal communities pump water out of the ground. That does two things. It lowers the ground, by the way, and the amount of fresh water that's available is a balance between the fresh water flowing in from the continental side and the ocean rising on the other side. And so they actually lose their fresh water as that lens, that battleground between fresh and salt water pushes inland. They lose their fresh water supplies. There are political tipping points. I was really interested to see this. This is a recent article in Newsweek. South Florida City Council votes to secede from Florida, citing rising seas. I found that really interesting because I immediately mapped this, which is the area that they want to make into New Florida, or whatever it's called, onto the area that is heading towards inundation. And you can sort of see why these folks up here in Tallahassee are saying, well, I don't really care because it's, they're all going to be below water anyway. Don't worry about them. Now, we've talked about this before, but this is a really important point to understand. The Earth has now 400 parts per million CO2. We don't have a 400 parts per million CO2 climate. And that's because we live on a water planet. So the dynamic range of sea level is one of those things that we try to get people to understand that they don't understand. The other thing we try to get them to understand is because you live on a water planet, do not expect climate to change rapidly. 90% of the heat that's trapped in the atmosphere goes to warming the ocean up. There's a lot of ocean to warm up. Now, once the ocean's warm, the planet's going to stay warm. So there's a downside to warming the ocean up. We know that roughly the equilibrium point, so if you leave 400 parts per million CO2 in the atmosphere for a long enough period of time, we ought to end up with about 2 degree warmer planet. This is the IPCC forecast, by the way, for 2100 out here. And that ought to lead to somewhere around a 15 to 20 meter high sea level on the planet. The physics of sea level rise are, again, so simple. It's a question of you warm the ocean, it thermally expands. You warm the air, you warm the ocean, it melts land ice. And you just get this trade between land ice and the ocean going back and forth. And that's actually what you're seeing here. As the planet warms up, you melt land ice. As the planet cools off, you make more land ice. You can make a prodigious amount of land ice, enough to lower sea level by 130 meters. If you melt all the land ice, so if you go back 40 million years, you get about 80 meters higher sea level. And that's when you didn't have Antarctica, you didn't have Greenland, et cetera. It was too warm to have those places. There's other ways to plot this. I like this particular graph. It's a little bit harder to understand, but this is basically a CO2 forcing or climate or temperature forcing function versus relative sea level. What this shows, excuse me, basically is that This is the, if you raise, this is the pre-industrial CO2 level, that as you raise CO2, you raise sea level by about 14, 15 meters. There seems to be a stability point. There's lots of air bars on here, but it's some sort of stability point around 15 to 20 meters. And then that stability point kind of falls apart when you reach somewhere around 600 parts per million. This is when Greenland and Antarctica shed ice. This is when East Antarctica begins to shed ice. So that's an interesting observation, because we're at 400 today. We will make 600. And we'll probably make more than 600 as time goes by. And so, at some point, we reach enough greenhouse gas collected in the atmosphere to warm the planet enough that we get back to that 40 million years ago temperature, which means no Antarctica and a ultimate sea level rise of about 80 meters. It takes centuries to achieve such a thing, if not millennia, to melt all of Antarctica. But one of the interesting things is when we look around the world, we don't see points down here. And we don't see points up in here. You see points here when it's cold, low sea level. You see points up here when it's warm, high sea level. We don't see a world in which you can have warm and low sea level. That doesn't exist because you're trading land ice for ocean. Right? So what does 13 meters of sea level look like? We've talked about this before. This is the reason why the Pentagon's interested and very interested. There are hundreds of millions of people who are going to have to move. This is climate refugees. We've seen what happens when you pour huge numbers of people into smaller and smaller areas, and they do not have water, and they do not have food, and Peter will talk about this more. He's an expert on this. This is, the results aren't good. Right? And we talk about terrorism. Really, ultimately, a lot of these things go back to the problems that we have where we can put people. Some interesting places where water accumulates. It turns out that the Sacramento Valley, I showed this at AGU, the American Geophysical Union here in San Francisco, the Sacramento Valley here, or the Great Valley where we grow lots of fruits and veggies. There is an opportunity to dam this up here at the Carquinez Passes, and we'll probably do that. But that means we become more and more Netherlands-like, where you're really heavily dependent on infrastructure to have your life. Because if that dam fails and the water goes in there, no matter what you think about Sacramento as a garden spot on the planet, there's a lot of food that's grown around this area. We've talked about this before, but this is 20 meters of sea level rise. There's a huge cultural loss here in Louisiana. This is a wonderful place. It's going away, and it's going away very rapidly as time goes by. Here's southern Florida with 20 meters of sea level rise. A lot of really interesting, as I pointed out before, some good fishing down here in the abandoned buildings of Miami and Fort Lauderdale, etc. So just clean up when you're done and get all the oil and gas and nuclear stuff out of there, and the rest of us will be happy with you. And then we've also pointed out here that, for those of us who are new to the conference, I'll let you guess what's really important about this part of the world. Disney, absolutely. So Disney World is right here, and Disney World remains high and dry with the loss of Greenland and the loss of West Antarctica, and that's a good thing. And you can actually sail all the Disney cruise ships right up to the Magic Kingdom, Port Disney.
Which ironically was built on landfill.
Yeah, but built high enough. Exactly. Yeah. What you got to do is think going up. And then this is when I give talks, I always have to show this. This is what state, class? And what was the first state? Delaware. First in, first out. You folks get it. For those of you watching online, if you remember nothing of my talk, you will remember FIFO. First in, first out. First in, first out. So Delaware we'll go back to 49 at that point, and then
Satterfield needs to get a new station.
Yep, we'll have to deal with this.
What about the New York City area?
We can talk about that. I got some slides on it. I did want to point, so as I like to troll the internet for examples of how people are trying to understand this issue of sea level rise. And this was one that caught my eye. This is from dogsports.com, which is a website for University of Georgia football fans. Now, for those of you who know anything about football, particularly Southeastern Conference football, I mean, this is in their blood. They don't like each other, right? So here is, chomp this, a few things every Georgia fan should know about Florida. USGS predicts that if ice caps were to melt completely, sea level would rise by approximately 80 meters. Got it right. If we can get the polar ice caps to melt only halfway, sea level will rise 40 meters. Another. And the face of the earth will change forever. So here's Florida with 40 meters of sea level rise. Now is the time, Georgia fans. Trade in those efficient vehicles for a gas guzzler. Spray some aerosol. That turns out to be wrong, but this is 80% right, for crying out loud. Burn as much coal as possible. We can make Florida a thing of the past. Now, I would submit to you, and I'll probably get yelled at for this, but the average reader of dogsports.com probably doesn't think that climate change is a big deal if they think it's real at all. But if climate change is going to mean that Georgia can make Florida obsolete, then by God, this is something we believe in, right? This is important stuff. So if you're having trouble getting through, try reframing the conversation. I didn't have to do this. These folks reframed the conversation for me. Obviously now it's time to take steps. One of the things we talk about in the Abrupt Climate Change Report is towards an early warning system. I won't dwell on that. I do want to give you some final thoughts. This is my granddaughter. About a couple weeks ago, the bathrobe is just to die for. That's Emmy. But so every public talk that I showed you, including the one down in Denver, I end on this. And this is what I think is becoming, to me, the big ticket item. And that is, what is the role of ethics? What is the role of morals in shaping how we view climate change, how we view a lot of these problems that we face? So thought number one, we say we love our kids, but do we show it? As I pointed out, we live on a water planet. Water planet means that it takes 50 to 100 years for the planet to react to what we do. So we have to think about that. The 400 ppm of CO2 we have in the atmosphere is a fundamentally different world than what we have today. And we're going there in our kids' and grandkids' lifetimes unless, for example, we actively take that CO2 back out of the atmosphere. Because the impacts come after the causes by 50 years or more, it creates an intergenerational problem. And we can say we love our kids all we want, but unless we actually show it, unless we're thinking 50 years down the road, we're not going to really make that much of a difference. So basically, this problem continues until one generation says, we don't need the short-term profits as much as we need the long-term stability for our kids. Right? That's really a challenge. The second thing I want to talk about is population. I've talked about this before, but as I said, I finished with these 3 slides. Population's got to be controlled. You can't have 9, 10, 15 billion people and expect for this system to function, right? Particularly 9, 10, 15 billion people using resources the way that we use them. So the best and most lasting way to control population, and you can talk to demographers and they will tell you this, is to empower women. So we live on a planet that has been male-dominated for a long time, and in many parts of the world, the value of a woman is equal to how many kids that woman has and how much labor she can produce in the fields. Right. In societies where women have economic value and where they have political value, birth rates among women go down. And that's just a fact of life. And that's just reality, because when women have value beyond having babies, when they are part of the political machine, when they're part of the economic machine, then you will have only 1 or 2 kids, right? Because there's other things to do out there other than to keep having kids, right? So, as I said, we live in a world that is still very male-dominated. The United States, yes, we've not had a female president. We allowed women to vote back in the early 1900s. It's not been that long. The world has, this has been slow to change. And change has got to come if we're going to deal with population. The third thing is you got to care about the poorest of the poor. And I've, again, said this before. You can't have 2 billion people living in poverty so deep that the health of the environment is not a consideration. If they are out there trying to get food and shelter for their children, they don't care about CO2. They don't care about sea level rise. They don't care about over-mining lithium. They don't care about any of these things. They're going to exploit what they have to exploit in order to live. And so you've got to consider wealth equity on the planet in some way. I mean, I'm not talking about making it all equal. I'm talking about you can't have the basement be so low that 2 billion people don't care. And that is a fundamental problem. So I will stop there. I will leave it on that slide and take any questions you have. Thanks for listening.
Jim, thanks very much. We'll open the floor right now for questions. There's a couple of microphones scattered about, but please raise your hand and we'll get a microphone to you. And just a reminder for the online viewers, we're going to bring Dr. White, Jim back, and also James Baylog to answer questions online. So if we don't get to your questions in this period before we take a break, we'll get to them when we bring them up front. So who's going first in the room? Who has a question? Jim, you got a microphone?
Yeah, I got one right here. Jim
Yeah.
Cantori, Weather Channel.
Yeah.
Great talk, Jimmy, as always.
Thank you.
Informative. Let's talk about Antarctica because of
Okay.
the ice expansion rather than depletion.
Yeah.
What's going on there?
Antarctica has seen an expansion of sea ice. And that is a lot of it we don't understand. Some of it we do understand. Some of it has to do with the circulation of the ocean and the freshening of the system out there. The fact that Antarctic sea ice expands doesn't say that Antarctica is getting colder, right? All it says is the conditions favoring sea ice formation out in the oceans around Antarctica are such that you're getting an expansion of ice. Right? Keep in mind that Antarctica is still a very cold place, and you can make sea ice. It's like in the Arctic. The Arctic may be getting warmer and warmer and warmer, but you're still going to have ice in the wintertime. Right? So yes, it's true that Antarctic sea ice has been expanding in some ways that we don't completely understand. We can give you a whole talk on that. But that doesn't then turn around and say that, greenhouse gases don't cause climate change.
Brad?
Brad Panovich, NBC Charlotte. I find interesting topic when I talk to the public about climate change. And if you get on the CO2, sometimes you lose people. But I wonder if we don't sometimes focus on other impacts. And I thought you brought up population, land use change, and disruption of the water cycle. Because to me, this is the easy sell to at least my local constituents of, hey, we're paving over what used to be, forest and trees, and we've dammed up a lot of our rivers here. And we've disrupted at least the water cycle locally, especially in the southeast with the population growth, that water's running off now. It's not getting back into the ground. So I'm curious, how much you looked into land use change and water cycle disruption is having a major impact.
We have, and the I think one of the things that is really I'd like to get people to understand is that climate change is really just a small part of the human impact on the planet. I call it training wheels for sustainability. So some of the other things I talked about in terms of fresh water, food, etc., these are also impacts that we have on the planet that are not necessarily tied back to climate change. They would still have those impacts whether climate was changing or not. And to get wrapped around the axle of climate change, to get your shorts all in a wad about that, and miss the important points that you just mentioned, that the more people you have using fresh water, let's say that the amount of rain stays constant. Let's say climate change doesn't impact the amount of rain in the southeast. You're still going to have more and more droughts, because droughts are defined now by how much water we need rather than how much rain falls from the sky. Right? So just understanding that human beings are a big part of the planet is step number one, I think, to getting people to understand not only climate change, which is just, like I said, a piece of the problem.
Yeah, and that's what I think. I think it is a gateway to get people to understand the impacts they're having, and then you can get into here's how you're having other impacts.
Yeah, I think, the reason why I talk about groundwater in what was otherwise a climate talk is because, in part it's because, yes, as climate changes, recharge rates change, and some of these, dropping aquifers may actually grow in areas where you get more rainfall. But, that's an impact that human beings are having. And we would have that impact whether you had a change in baseline of precipitation or not. In many of these areas, there's been no change in how much rainfall falls or snow falls. But
Jim, Joe Murgo from WTAJ, Altoona, Pennsylvania. When is the threshold where we stop pushing the money into the research to prove to a very minority then that something's going to happen. I mean, the best thing that I heard today is that we're planning on maybe a dam. When are we going to start putting our resources instead of, okay, we're going to argue how, when are we going to start putting our resources to adapting to future changes? If we're saying that also a lot is not going to be able to be changed, are we starting to convince the government, don't build this here? Let's start working on something that's going to take 50 years to survive.
Yeah, thanks for the question. It's interesting because it's already happening in ways that we don't see, because it may be happening with someone siting a new power plant or siting a new water treatment plant or building an air conditioning system for Google or for Microsoft. They're looking at what's coming down the road. They're accepting the science and saying, okay, here's where sea level's going to be. I can't build my water treatment plant on Long Island where I was thinking of it because I want that water treatment plant to last for 100 years, and in 100 years, that place is going to be, threatened by rising sea level. So let's put it someplace else. People are beginning to think about this. I would say that, unfortunately, 60 years out or 40 years out are about as far as any political group wants to think about adaptation. And that runs into a roadblock that many of the things I talked about are happening slowly. They're inevitable. They're going to happen. Sea level is going to be 10, 20, 30 feet higher, but it's going to happen slowly. And so how do you match that? I care about the next 10 years with what's inevitably going to happen.
I think we need to start publicizing the events when a decision is made like that.
Yeah.
I think people in the science community who are involved in making that decision need to start publicizing, hey, we did this instead of this, because that to me may be more eye-opening to the average person.
I would point out that one of the things that we called for in this report was basically coordinating and enhancing our just plain monitoring of the planet. And this is something you folks know that the amount of places where we actually observe the planet and temperature and precipitation and sea ice extent. For example, we don't monitor temperatures of the ocean down around Antarctica, which is a critical place to understand temperatures if you want to understand how the Antarctic sea ice is going to behave. So, one of the analogies I make in the report is that, there are cameras everywhere. There are cameras on street corners. There are cameras in banks. There are cameras in grocery stores. Every night on the evening news, you see, some clown who thinks they can rob something without a camera watching him. Cameras are everywhere. We don't spend nearly the amount of money monitoring the planet, which provides us with food, water, etc. Right? We don't have those cameras. We have satellites, yes, but even with the billions that are spent on satellites, it's nothing compared to the amount of money we spend watching ourselves. Yeah.
Jim, Jennifer Cavina from Local 6 in Paducah. We got James' perspective on the political arena a little bit. I live in Kentucky where Mitch McConnell obviously is a big player.
Yeah.
And everything is the message of war on coal. It was already hard enough to battle the climate change view in my area. And now it seems like it's going to get even harder in the next couple of years. Have you noticed any kind of shift in the political arena at all that might give me hope for some kind of, at least are they open to listening? Have you seen any kind of change?
Well, you had me until that might give me hope. I've seen a shift. I think it's what we've seen in the last 10 years has been a real hardening of the position that climate change is not real. And a real, I would say, an increase in using the PR machine to make points that you and I, if you dig into it just a little bit, know that that point is not realistic. For example, if coal, yes, has been decreasing as an energy supply. We call it a war on coal. Is it climate change that's causing a war on coal? No, it's natural gas. It's fracking. It's the ability to pull those resources out of the ground more cheaply that is actually impacting coal. And so the PR machine is spinning this as a conflict between climate change and coal, when really that's not been the driver at all of the decrease in the price of coal, a decrease in the mining of coal. It's been more, what we've seen, this remarkable change in how we get oil and gas out of the ground and how that's gotten so much cheaper and how that's changing things.
Are they digging in?
I think they are digging in. I think the next 2 years will be really interesting. We heard a couple of talks from folks from NOAA and talking about NASA. So I believe I have this right. The head of the subcommittee for NOAA, that funds NOAA, will be Marco Rubio, I think, who doesn't believe that climate change is real. And the head of the subcommittee for funding NASA is Ted Cruz, who also doesn't believe that climate change is real. So it's going to be an interesting ride here, And for those of us who, my own personal fear in this is that, for those of us doing basic research on how the climate system functions, and we're nervous. Ignorance is never bliss. I don't think it's a good idea to put on blinders when you've got problems coming. And that, I think, is really the situation we find ourselves in today. We ought to be spending more money monitoring things. We ought to be watching the system more carefully so that when tipping points come or just change comes, we understand that better, rather than saying, no, we don't have a problem.
And finally, how do you communicate this is not a political issue? I think that's the biggest thing, because it doesn't matter what my beliefs are politically. They certainly aren't in line with how I tend to vote, and I don't mind saying that.
Yeah.
But I can say that, and they still don't listen. So
No.
how do you make this non-political?
Well, what I try to do is what I talked about, in depth here, we talk about laws and stuff like that. What I talk about when I talk about in public is I say, look, there are physical things that you cannot get around. Nobody thinks that they can disobey gravity. And we've done this in this room where we have a little exercise. I'll put somebody up on a chair, and I'll say, if I push, Jennifer off this chair, what'll happen? And no one ever says that you won't fall. They always say you're going to fall. It's a question of how hard you're going to fall and what are you going to break along the way, right? So we know they're physical realities. Greenhouse gases absorb energy. That's what they do. They can't do anything else. You don't get to believe or not believe in climate change. You can believe or not believe that we can do something about it. You can believe or not believe that it's something we should address. You can believe or not believe that it's an economic problem versus an ethical or moral problem. Beliefs apply all there, but you do not get the option of believing that climate is changing and that human beings are causing it, because that's physical reality. Jay.
Jim Rader, Wichita.
Yeah. Can I wander over here?
Not too close, Doctor.
Yeah.
You brought up very early on the population curve.
Yeah.
Humans require food, fuel, fiber.
Right.
We're not using carbon-based fuels because of big industry. It's because they're compact, they're robust, they're inexpensive.
Right.
All the focus we see politically is strictly on carbon and the fuel industry, yet the elephant in the room driving everything is population. When is the population component going to be as forefront as carbon?
I think in the next 20 to 50 years, I think a lot of the other features that we talked about in terms of challenge of sustainability have got to come to the fore. And population has got to be a big part of that. Like I said, you can't have 15 billion people and have the kind of lifestyle we have and have the system function. I think that's just becoming a reality for us. Here's my hope as an optimist. My hope is that we use this challenge of climate change to learn how to cooperate internationally, because we share an atmosphere. It doesn't matter if we quit burning fossil fuels, which would be economic craziness, but if we did it and China continued to do it, CO2 is still going to go up, right? We need to understand that if we're going to deal with climate change, we've got to learn how to deal with the fact that we've parsed the world out into countries and learned how to deal with international issues. If you learn that, then a lot of other issues get easier. So it gets easier to address population, because that's got to be an international issue. It gets easier to address water, fresh water, which is frequently an international issue. It gets easier to address food, which has become an international issue. So I see these things as stepping stones towards dealing with these thornier and thornier problems as time goes by. We've got to deal with them.
So, Erin Robinson, Foundation for Earth Science. I really liked this pairing of talks of James and then your talk following up. And in James' talk, he said, that humans feel really small. And then you had this great slide about how big humans are. And it was this reframing that you did, and it was, I don't think maybe you were even thinking about it as a reframing, but sharing with people that our collective impact is so big might be one way that we move toward this international cooperation that you're talking about. But I wondered if you have more thoughts on humans being big, because for me that was really eye-opening, and I work in earth science.
No, I think what you've put your finger on here is a real sort of fundamental problem we have, because most of the world today sees humans as an insignificant part of the planet. And I would say most of the decision makers around the planet see themselves as kind of small. And I got this. I mean, we have the same discussions at Thanksgiving as you probably do, where, some people at the table say there's no way that human beings could be causing climate change because we're not that big. And yet, if you look at the reality, if you look at energy, if you look at fresh water, we use 70-something%, 75% of all the available fresh water on the surface of the planet. There's no headroom there, right? We use nitrogen, we're big. Sulfur, we're big. There's really not a cycle on the planet, even the rock cycle, for crying out loud. We move more dirt. This is one of those things that's happened very quickly because of that population curve. And it's one of those new realities. It's, understanding how our planet functions is an absolutely critical thing for the kids going forward. If they don't understand that, then they'll make the same mistakes in terms of water, in terms of the natural period of the planet being 50 years or more when it comes to climate change, stuff like that. We need to understand how we really fit on the planet. I agree with you. Like I said, maybe we have to have a generation or two die off before we get to that, but the problem is that we're at 400 ppm CO2 today. And I'd be willing to start taking bets that we'll make 600 without a problem.
And John Morales from NBC6 in Miami.
Miami.
Ground zero, #1 city in the world in terms of exposed infrastructure and property values
Absolutely.
To sea level rise.
Yeah.
So I, quite knowledgeable about this. I'm constantly, talking about this down in South Florida. And South Florida, at least at the local level, in some some of the municipalities down there are trying to take some steps. But my question to you is as follows. When they look at this problem, they look to the year 2050 and the year 2060 because generally speaking, architects and engineers and city planners all only worry about the 30 or 50 year lifespan of buildings or sewer lines or what it may be. Mm-hmm. So in planning for this, they're planning for about 82 centimeters, which is 2.7 feet in the case of Miami Beach. The Southeast Regional Climate Compact is planning for 2 feet by the year 2060. But, 2 to 2.7 feet could just be the tip of the iceberg, no pun intended, of where we're headed.
Yeah.
How do we get the local planners and politicians to realize that this isn't just what's going to happen between now and 2050?
John, that's the exact same question I ask myself a lot these days. How do we get people to understand the inevitability part of this so that they're not just planning for 2050 and saying, okay, we'll deal with it then? I think, to give you, let's pick on another city for a minute. Let's pick on Manhattan, New York City. They're talking about building a wall around southern Manhattan, all the way around, which will have all sorts of beautiful, pedestrian parks and stuff like that. I don't know what the cost is, but it's got to be very large, billions. They're going to end up with a wall underwater at some point. And how do you get people to understand that, yes, you can fight, but unless you view this as the long-term fight, as the fight for the next 100, 200, 300 years, then you don't get the big picture. You don't understand the reality of this. Now, on the other hand, short term, there's a lot of money made in the short term. And understanding that human beings think short term is another thing that we have to, those of us who think 50, 60 years down the road, have to understand that, yes, a lot's going to happen between then and now. People are going to make gobs of money. People are going to lose gobs of money. All that stuff's going to happen. Life is going to go on at the, year to day to 10, 15-year time scale. And we have to live through it. But I agree with you. This is one of the biggest challenges that I've seen, that particularly for sea level rise, not only in Florida, but in Virginia, in New York, and in other areas. People just don't really want to, or they're unable to grasp the inevitability factor. And maybe there are things that we need to do that build well beyond that. I wish I had an answer to you. But I ponder the same question frequently.
Jim, thanks. We have one more question before we take a break, and then we'll take questions from the internet audience after we set up the chairs. We're running a little bit over, but as you can see, the discussion is dynamic and interactive. Kent?
Kent Earhart from KMOV in St. Louis. Jim, you touched on this a little bit in regards to mitigation and adaptability, and you've talked about this in the past. What do you see as the impact and perhaps more importantly the opportunities as an academic when you talk to students for employment in the future and jobs and where people should be looking to exploit the inevitable?
Well, that's a great question, Kent, and I think that there's a huge opportunity there. It's kind of, interesting and ironic that we mess things up and then we pay to fix them. But, that's the way the economy works, right? Sometimes you do one thing that then you have to do another thing to fix it, and you still make money in the process. Jobs in the environment have held up throughout the economic downturn, throughout the global downturn. Jobs in the environment have held up because the problems aren't going away. And indeed, if I put on my hat and look at my crystal ball for the next 100 years, those are the biggest problems to face in the next 100 years. How are we going to deal with food, with population, with all those other things? And we're going to need a lot of well-educated, smart, dynamic people working on these problems, and they're going to make money doing it. And God bless them. I hope they turn around and give money to the University of Colorado. But, I think that's, there's the good news of this, the silver lining of this, is that, there's money to be made. And where there's money to be made, you will attract people. You will attract entrepreneurs.
So maybe it's not so much a point of what areas you would recommend for students to pursue as much as including climate change education across the board, so that people like civil engineers are planning for that, like you talked to, John, with the in regards to civil engineering in Miami in 60 years.
So one of the interesting things, when you talk to the business community, it's not really they don't care so much that climate is changing, or they just want to know what the rules are. If you know what the rules are, then you can start a business and you can compete successfully, because most people who go into business think that they're really damn good at what they're going to do. But if the rules are constantly changing, it's hard for anybody, no matter how smart they are, to move forward. I think by accepting science, by building the rules around solid science and inevitabilities, then you can build those rules to be more robust, and you can have a more robust economy going into the future.
Jim, thank you very much. This has been terrific.
Thank you.